Yeah, so ionic and covalent bonding will be the order of the day. So, does anyone have any questions? Of course, be sure and log into Blackboard, do your attendance true false exam, and then after today's lecture, go in and do the assignment for the online today of something you picked up, or answer one of those questions in the online quiz. And I will get those uploaded. And had a nice little group on for tutoring on Tuesday, so that was good to see. I think it was helpful for those who showed up. So yeah, nice group. Good to see everyone. All right. Does anyone have any questions or comments? Because I think I will just plow right in and get through as much as I can in the next 45 to 50 minutes. If no one has any issues or concerns. Okay. So let's get that and that. That's where I looked at it by just previewing my lecture there today. Can everyone see the lecture, the slide deck on the left, and my whiteboard on the right? That looks good. Oh, excellent, good deal. Okay, so, and I do want to look, see how we're doing. As far as good online attendance, I'm only missing one of the people who were in class. I have not logged in and done that. So great, good. Oh, this is two. Okay, let me clear that out to let you. Okay, so that should allow you to get back in. Let me know if you have any issues with that. Okay, so ions essentially. So we had kind of touched on these when we were talking about elements last week, but when things are neutral, you have an equal number of protons and neutrons. Now we're going to get into the situation where things get a little more interesting, where you have differing both positive and negative charges or ions. Okay, so an ion by definition is something that has a positive or negative charge. Okay, there are two types of bonds. Atoms lose, gain, or share our friends' valence electrons to acquire that octet that we've been mentioning, so that they are happy having an octet in their outside shell. Okay, so ionic bonds are when the atoms of one element actually lose electrons and the other atom that it's forming a bond with gains that electron. So it's actually transferred all the way, and then it produces a positive negative ion that then have an attraction to another. Okay, and covalent bonds are when non-metal atoms actually share the electrons to attain that noble gas or octet. Okay, the covalent bonds are a little stronger because you're sharing, and the ionic bonds tend to be able to break apart much more easily. Okay, so here's a visualization of what's actually going on here. We have a non-metal in blue on the left. Excuse me, we have a metal, pardon me, back that up. I have a metal in blue on the left and a non-metal. It's not namibium or anything. It's a non-metal. And we are actually transferring that valence electron from the metal to the non-metal, which needs one electron. And now, if you follow the arrow down, the nonmetal now has a negative charge because it has what? An extra electron as opposed to its number of protons. And the metal that has lost its electron now has a positive charge because it has one less electron, which it has given to the nonmetal. Okay, so now you have an ionic bond between the metal and the nonmetal. Okay. In a covalent bond, you are sharing electrons between two nonmetals. So in our example, we have two nonmetals that have 7 valence electrons. They each share one of those electrons to form that covalent bond. So there are 1, 2, 3, 4, 5, 6, 7, 8 around each nonmetal due to sharing in a covalent bond. Okay, ionic, metal and a nonmetal, covalent, a nonmetal and a nonmetal sharing. Okay, that's the big picture version of what's going on when we're looking at ionic and covalent bonds. Okay, so now knowledge of our periodic table is going to start coming in and start paying dividends right now. Our metals are in groups 1A, 2A, and 3A. If you have your chart out, that's on the far left, 1A, 2A, and you skip all the way across the middle part to get to 3A. Those are the metal groups. Okay, so they are the ones that are going to want to give up their electrons to form that octet. All right. So they will readily lose those electrons, and those electrons are easy to knock off, so they tend to have lower ionization energies. Those electrons are easily shared because they want to get rid of them and they want to get stable. Okay. So just some quick kind of math, I guess, or conceptual math at least. If something is neutral, here we have a sodium, which in its neutral state has 11 protons and 11 electrons balancing each other's out. Sodium, as you can see, is in group 1A. It has 1 valence electron. If it gets rid of that valence electron, it loses a negative charge, and now you are left with an ion that is positive of 1 because it has lost 1 electron due to the ionic bond. So now you went from a neutral sodium to a sodium ion with a positive 1 charge due to that loss of the electron. Okay, so sodium is a metal. So far, so good? Okay. So let's look at just another group. We'll look at a metal in group A, magnesium. In this case, it has 2 valence electrons. So what is it going to want to do? Of course, it is going to want to give up 2 electrons to become stable. If it loses 2 electrons, it forms a +2 ion. Okay, it went from neutral, lost 2 electrons, and now has a positive charge of 2. Okay, the loss of 2 electrons. Okay, so that's group 1A, 2A, and 3A, all the metals giving up either 1, 2, or 3 electrons, forming ions with +1, +2, or +3, depending on the group and the number of loss of valence electrons, groups 1, 2, and 3. Okay, so the non-metals, so we skip group 4. We'll come back to group 4, especially in organic chemistry. We skip group 4. What do we have there? Brenda. We skip group 4 and go all the way to group 5A, 6A, and 7A, which have, by definition, 5 valence electrons, 6 valence electrons, and lastly, 7 valence electrons. Okay, 5, 6, and 7. So nonmetals, like we had mentioned, to get happy and get their octet, they are going to want to steal or take those electrons from a metal to fill up that shell. Okay. So the metals are giving up their electrons. Groups 5, 6, and 7A want to take on those electrons. So just like when losing an electron in metal gave you a positive, if you take on electrons, you are going to have a negative charge. Okay, so let's look at chlorine, which is in group 7A. It has, of course, 7 valence electrons. It wants exactly 1 electron from a metal to make it happy. once it takes on that electron, it goes from neutral and having 7 valence electron to being a negative ion, chlorine minus 1 technically, with its 8 valence electrons. Okay, so that's the non-metal. What the non-metals groups 5, 6, and 7a all want to do is take on electrons from metals and become negative ions so that they can form ionic bonds with the metals. Okay. So this is just a review of all of the stuff that's on your periodic table, group 1a, 2a, and 3a, and their cation, which are positive. Okay, they've lost 1 electron in each of these cases to become lithium, sodium, and potassium plus 1. They lost that 1 valence electron. Magnesium, calcium, and barium, they have lost those 2 valence electrons to become a cation with a charge of 2. And aluminum is our last example. It lost its 3 valence electrons to get a cation charge of plus 3. Anions are a negative ion, so that's fairly easy to remember, right? A negative ion. And groups 5, 6, and 7, we have, let's look at phosphorus. So it's going to take on 3 electrons and become an anion with a charge of negative 3. Oxygen and sulfur will both take on 2 electrons to get a charge of negative 2 to be happy. So they be anions with a negative 2 charge. And fluorine, chlorine, bromine, and iodine will all take on 1 electron to go from 7 to 8 valence electrons, and that ion with a charge of negative 1. Okay, so everything in the right, the non-metal, is taking electrons from the metals on the left to become their respective anions and cations. Okay. And it's just a visual representation of that. I'm not going to go into that slide too much, but yeah. Those are groups 1, 2, and 3a, and 5, 6, and 7a, giving up electrons on the left, taking on electrons on the right, becoming cations on the left, and becoming anions on the right in our ionic charge. Okay, yes, of course. These you see this all the time when you're looking at anatomy, various ions, sodium, of course, salt, sodium chloride, salt, calcium, magnesium, all these things. Okay. So here's just to make sure that we're following along. We have a symbol of an ion with 16 protons and 18 electrons. Okay, so go to a chart that has 16 protons. Look on our periodic table, we see that is sulfur. Okay, and 18 electrons. So it has 16 protons. It has 18 electrons, so it has 2 extra electrons. So we know that we have a charge of negative 2. Sulfur, anion with a charge of negative 2. Okay. And let's see here. So let's look really quickly. Proof of mastery here. Calcium and chloride, which is a metal and which is a non-metal. Okay, go down. Calcium is a metal. Chlorine is a non-metal. Valence electrons, just look at the group they're in, and it will spit out, it will tell you the number of valence electrons if you don't know that off the top of your head. And you're allowed to use that on your tests and quizzes. Okay. So two valence electrons and 7 valence electrons, group 2a and group 7a, respectively. The number of electrons that must be lost or gained. I think I'm just going to go down here. Lost or gained. Calcium will lose 2 electrons. okay, because it has that 2 valence electron. It's going to lose those 2, and chlorine will gain 1 to acquire its octet. Okay, so the calcium in D, when it loses its 2 valence electrons, becomes a cation with a charge of +2. Chloride gains that electron to get a charge of -1. Okay. It is, and it will depend, and it does a lot more covalent bonding. Yeah, group 4 doesn't get used. I don't think it's used at all in ionic bonding. So it's covalent bond because you're exactly right. It's going to basically form 4 covalent bonds. Okay, and ionic bonds, groups 1 through 3 and 5 through 7. And of course, 8 is already happy and non-reactive. Okay, so let's look at our probably the ionic bond that we are most familiar with, sodium chloride or salt, table salt. Okay, ionic bonds have high melting points. Okay, and they're generally solid at room temperature. So sodium is a metal in pure form, ductile, silvery, and chlorine is actually a very poisonous gas at room temperature. But you put them together and you get sodium chloride via the ionic bond between sodium and chloride. Okay, and here's an example. Here is the representation of what's happening. We have sodium with its 1 valence electron and chlorine with its 7 valence electron. Sodium gives up that electron, becomes a +1 in the ionic bond. Chlorine takes on the electron from sodium, becomes a -1, and you have sodium chloride. Okay. So it's not always 1-to-1. So I'm going to draw this out. So we have magnesium, which is in group 2A, okay, and chloride. So magnesium is group 2A, so it's going to want to give up 2 electrons to get happy. So its ionic form is -2. Okay. And chloride, that's a terrible. Chloride, as we already mentioned, will have a +1 because it, I went backwards here. Magnesium would be a +2, sorry, and chloride is a -1. There we go. In their ionized form to form the ionic bond. So since magnesium wants to give up 2 electrons and chloride wants to gain an electron, the formal form of that is 1 magnesium atom and 2 chloride atoms, or magnesium chloride. Okay, balanced out the 2. Mm-hmm. Yeah. Okay. So tell you what, if you're looking at it and you actually don't have it, circle back to me, and I'd be happy to explain it. Yeah. 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 So you're just balancing out charges between your metals and your nonmetals, essentially, to form a molecule. Okay. So here is another example. We have sodium, which is group 1A, has its 1 valence electron, and sulfur, which has 6, group 6A. Yeah, I had to double check. Group 6A. So sulfur is going to want 2 of electrons. It'll take 1 electron from one sodium atom, one electron from another sodium atom. Then we'll have sulfur anion bonded to two sodium cations. Okay, and our balance is charged up. Two negatives and two positive charges. Okay, so the ionic formula of a compound formed with barium, okay, and chloride, of course. Okay, so we have our metal and our non-metal. I'll just start sorry. The metal always goes first. So we have barium and then chloride, subscript 2 to indicate that you need the two chlorides to form that molecule, barium chloride. Exactly. If you look on your periodic table, barium is in group 2A. It's got two valence electrons. It wants to give up two negative charges or two electrons. Once it does that, it takes on a charge of +2. Okay, good. So barium chloride, barium chloride. Okay. So let's just look here. If we're going to combine sodium and oxygen, which one of those is the correct molecule that's going to form with an ionic bond with ionic bonds? Okay, so in the first case, it would be sodium oxide number 2, because we need the two plus charges to balance out the two negative charges on oxygen. So you need two of the sodiums and one of the oxygen to balance out those charges. Okay. Likewise for B, we have aluminum, which is a cation with a +3, chlorine with a -1 charge, hopefully somewhat obviously at this point. So we will need three chloride negative charges to balance out the three positive charges on aluminum. So number one be aluminum chloride, sub 3. Okay. And the only tricky one here, let's look at this, magnesium and nitrogen. Okay. So we have magnesium, the 2 plus charge, and then nitride with a 3 negative. You can't just cram those together nice and easy. So follow along here, little arithmetic. If I have, and it gives you, you know it's not number one because they don't balance. If I have three magnesiums, and two nitrides, it gives me 3 times 2, or 6 positive charges. That's not very good. And right here, if I have two of those, 2 times 3 gives me 6 negative charges. Okay, so that's why I needed 3 magnesiums and 2 nitrides to balance out the 6 positives, cations, and the 6 negative charges. Yes. Yeah, because there aren't partial charges. You can't have magnesium 2.25, nitride 1.7, or whatever. The subscript, the number of charges will always be a whole number. So you're always going to have a whole number in your atom. Yeah, I mean, if that helps you visualize, yes. But I mean, but as long as you understand the reason for that happening, because we needed two of the nitrides to get to the 6 negative, and then we need 3 of the magnesiums to get to the 6 positives. Yep. Okay, and we did that, of course. Okay, so there is Morton's salt. Has some potassium iodide, so that we don't get goiters anymore if we use a little salt. Goiters used to be a thing from iodine deficiency, but now not only sodium chloride, but we'll put a little potassium iodide in there as well. So now you know why you don't have to deal with having goiters in your neck. All right, so naming these, I've already been kind of talking through this as I've been doing it. So when you want to name an ionic compound, you always put the metal first. Group 1, 2, or 3 is going to be the first element, just by convention. Don't ask me why. That's the way it is. Learn it, set it, and forget it. And the non-metal will go second, and you then add IDE to the end of it. Okay. Okay. So on the left, we have potassium, right? Which is group 1. That is the metal. Iodine. So potassium iodide. Magnesium is the metal. Bromine is the non-metal. Magnesium bromide. And lastly, the one we just looked at, aluminum and oxygen. Aluminum is the metal. Oxide is the non-metal. Aluminum oxide. Okay. And for ionic compounds, since there's only one ionization state they're ever in, you don't need to indicate how many, like aluminum aluminum trioxide or anything like that, because by definition it's going to be 2 aluminums and 3 oxygens and aluminum oxide. When we get to covalent bonds, not quite so straightforward. Okay, so ionic bonds, metal, non-metal, IDE. Okay, and that's just saying that. The non-metal. Oh, at the end of the non-metal. Okay, so let's do an instance. So we have, okay, metal potassium, non-metal oxygen. The name of that is going to be, of course, potassium, non-metal, ox, and then instead of oxygen, it's oxide. Okay. Okay, can anyone tell me what the name of the first, what A is? Calcium oxide, perfect. And we've already done aluminum oxide several times. How about C? Magnesium chloride. Okay. And there we go. Magnesium chloride. And there is, yeah, a several slide explanation of how you name ionic compounds. And let's see, where are we at? Oh man, we got a lot done. And then I'm going to circle, yeah, so we'll get through the metals with variable charge, because I'm going to answer, I didn't catch whose question that was about why we don't deal with the other groups. We said group 4, but there are other groups where there are issues as well. And we'll circle back tomorrow. So let's just fill out this chart just to make sure that we're driving this point home. Well, okay. Okay, so we're going to combine in the upper left-hand corner sodium and bromide. Well, already added it. So sodium and bromide. Okay, moving across. In the second case, we have sodium, the metal, and that only has one charge, so we're going to need two of those for our sulfide. Okay, sodium sulfide. And last but not least, we'll need three sodium anions or cations to go with the, oops, yes, sodiums to go with the nitride. Sodium, three of those to go with our -3 on the nitride. Okay, first row, 1, 2, 3. Okay, and let's look down here. We have aluminum as our metal, is a +3 cation. So we will need 1 aluminum and 3 bromides to form that, to balance out the charges. Aluminum bromide and aluminum sulfide. No, let's see, I need to do a little math. So aluminum, so I need 2 of those and 3 of those to balance out the charges of 6. So aluminum sulfide. So we have 6 charges on the aluminum portion and 6 negative charges on the sulfur, aluminum sulfide. And lastly, we have aluminum on its with its +3 and nitride with its -3. So aluminum nitride. Double check aluminum. Yes, if you don't know where it's at, then yeah, you'll have to refer and see if it's in group 1, 2, or 3. Um, but you'll also know if they're putting a positive that you're looking at a metal because because it's giving up electrons, right? The metals are all giving up electrons to become cations. Is another kind of rule of thumb, a shortcut to figure out which one is the metal. But yeah, but it's always good to know why it's a metal and where it is on the periodic table to explain what's going on chemically. Okay, so let me see. Oh, there's Derek. Oh, Derek. you missed you missed all the fun. Yeah, I had my screen covered up, so I couldn't see you when. Yeah. But good news is, with any luck, I have these lectures. I'm uploaded to YouTube. Sorry, and then I put the link in Blackboard, so you can go back and look at the lecture if you're not able to be in class or you're late or whatever. You can certainly do that. I'm basically for you guys, and this is a work in progress. This is my second time through chemistry. I am labeling them by subject. Yeah, so today's will be ionic bonding. Yep, yep. Okay, so I think that is a good spot.